In the problem from the last video, we calculated the amount of hydrogen gas necessary to completely consume an amount of SiHCl3. In this video, we're going to look at what happens when we use an excess of H2 gas and learn how to identify which reagent is in excess and which reagent is what's called limiting given a set of reaction conditions. We'll also look at the concept of percent yield to evaluate how well we did after running a chemical reaction. In the situation from the last problem, imagine we'd used more than the stoichiometric amount of H2 gas, more than the 0.326 grams that we calculated in the last video, with the same mass of SiHCl3. Would this lead to a larger yield of product? In fact, it will not. What will happen when we use, for example, 0.5 grams of H2 instead of 0.326 with the same mass of SiHCl3? Take a bit and think about this and try to describe the situation in your own words. In the meantime, I'll try to draw a picture of what's going on. We have some mass of SiHCl3 that we'd like to consume completely. And we know that a certain mass of hydrogen gas, which is considerably smaller, is what's called the stoichiometric amount. In the case of the example from the last video, this was 0.326 grams, and the mass of SiHCl3 was the 21.73 grams. If we tack on an additional, say, 0.174 grams of H2 onto the original stoichiometric amount, well, the only things that are going to react are all of the SiHCl3, which I'll just highlight in blue, and the stoichiometric or corresponding amount of H2, which is only the portion that's 0.326 grams, right? So when it's all said and done, we will have the corresponding amounts of product over here, along with the remaining chunk of H2 that didn't react. What this shows us is that H2 under these conditions is in excess. There's an excess above and beyond the stoichiometric amount that is not completely consumed. So once all of the SiHCl3 is consumed, we'll have that extra chunk of H2 remaining. Under these conditions, the SiHCl3 is completely consumed, and it's what we call limiting. It's limiting because if we added more SiHCl3, then we could push the 0.5 grams of hydrogen further along towards products. But under the conditions we've written out here in the second point, SiHCl3 limits the amount of product. No matter how much H2 we add to the reaction mixture, we can only get an amount of product that's dictated by the moles of SiHCl3 there. When it comes to limiting reactants, there are two key questions we'd like to be able to answer. First of all, how do we determine the limiting reactant given a set of reactant masses or amounts? And secondly, how do we determine the situation after the reaction has run its course, or once the limiting reagent has been completely used up? To begin to develop answers to these questions, I want to roll things back a little bit and talk about the units of stoichiometric coefficients and whether we can think of coefficients in a balanced chemical equation as having units at all. So let's return to this idea of a generic balanced chemical equation with coefficients little a, little b, little c, and little d, reactants A and B, and products C and D. Can we think of units for the stoichiometric coefficients here? On the one hand, they seem to just be counting molecules. But on the other hand, if we think of each occurrence, each iteration of this reaction as a single reaction event, then we can think of each coefficient as the particles of that reagent that react per reaction event. So each coefficient is a number of particles per reaction event, or a number of moles per mole of reaction events. And so I've written out two examples for A and B, but of course the same idea applies to C and D. This idea of a reaction event is actually quite useful for understanding limiting reagents, and it's a concept we'll return to again when we talk about thermodynamics and how to develop intensive thermodynamic parameters for chemical reactions. A reaction event is defined as a single occurrence of a reaction at the molecular level. In this video, we'll count them using the variable x, and you may also see me use the Greek letter z to represent a count of reaction events as well. So then we can think of each of the individual coefficients as a molar ratio in its own right, not to any other substance, but to a single reaction event. So the coefficient little a, for example, is the molar ratio between big A and the number of reaction events. What we can do then with a given set of reaction conditions is that we can use the stoichiometric coefficients and the given amounts, given numbers of moles, to determine a hypothetical number of reaction events that each reactant can engage in. To find each of these hypotheticals, what we're going to do is divide the given amount of each reagent by its corresponding stoichiometric coefficient in the balanced chemical equation. And there's a good reason for doing this that I hope to demonstrate in these two examples. So let's imagine that we had 0.3 moles of copper engaging in the reaction that's shown here and 0.45 moles of nitric acid, HNO3, and we're trying to determine which of these two reactants is limiting. Let's draw an analogy to this chemical reaction and think about making a sandwich. So let's imagine that to prepare a sandwich, we use 4 slices of ham, 2 slices of cheese, and 2 slices of bread to produce a single sandwich. And let's say that we had on hand 10 slices of ham, 8 slices of cheese, and 20 slices of bread. We can ask the exact same question for the sandwich making process that we asked for the chemical reaction up above. Given the amounts of ingredients in this case that we have on hand, how many sandwiches can we produce, and which ingredient is the one that's limiting the number of sandwiches that we can produce? What we can do with the bottom scenario is calculate the hypothetical number of sandwiches that we can produce given each of these ingredients and assuming an excess of all the other ingredients. It's the smallest one of these hypothetical x's that's going to be associated with the limiting reagent, or the limiting ingredient in this case, and we'll see why that is when we get to the end of the calculation. So the way to do this is to take the number of slices that we have on hand and divide by the number needed to produce a single sandwich. So if we have 10 slices of ham and we need 4 per sandwich, then that means that we can produce 2.5 sandwiches, just abbreviate that as sand, from this 10 slices of ham. For 8 slices of cheese, if we use 2 slices per sandwich, then we can get 4 sandwiches from the cheese. And for the bread, if we use 2 slices of bread per sandwich and we've got 20 slices of bread, we can make, in theory, 10 sandwiches from the bread we have available. Now that we've calculated these hypothetical numbers of sandwiches, it's clear that the maximum number of complete sandwiches we can make is 2.5. The ham is what's limiting the number of sandwiches we can make because it's associated with the smallest number of possible sandwiches that could be made. And so we'll find that the cheese and the bread are in excess and that the ham is the limiting ingredient for the sandwich making process described here. Now let's apply the exact same idea to the reaction of copper and nitric acid above. We've got 0.3 moles of copper, and we need 1 mole of copper for every mole of reaction events. So to calculate the moles of reaction events that copper can engage in here, we simply divide by 1 mole. This one here matches the stoichiometric coefficient that's right here, a 1 in front of the copper. And so we can get 0.3 moles of reaction events from the 0.3 moles of copper that we've got. For the HNO3, well, it takes 4 moles of HNO3 to engage in a single mole of reaction events. And so we need to divide this by 4 moles. And this 4 matches the stoichiometric coefficient here. Really, the units in the denominator here are moles per mole of reaction events. We can think of these stoichiometric coefficients as molar ratios or mole-mole ratios in their own right. Doing this division, we find that the nitric acid that's there can only engage in 0.113 moles of reaction events. And since the HNO3 can engage in fewer reaction events than the copper can, we know immediately that the HNO3 is the limiting reagent here. So notice what we did in each case. We calculated a hypothetical number of reaction events that each reactant could engage in. We needed conditions, we needed numbers of moles to do that, and so you'll be given, or you'll be able to calculate, moles of the reactants in order to determine the limiting reactant. And we looked at which of these is smaller. What we can say in general is that the limiting reagent will be associated with the smallest hypothetical X value, the smallest number of hypothetical reaction events. How much excess remains? In other words, what's the situation once all of the limiting reagent has been used up? We saw before that we can only make 2.5 sandwiches given the conditions we have here. Because the ham is limiting, and this will always be true, there will be no more ham left at the end of the sandwich making process. To find the amount of cheese left, we need only find the number of slices necessary to produce 2.5 sandwiches. So what we can do is multiply the 2.5 sandwiches by the number of cheese slices per sandwich to reveal that we need 5 slices to make the 2.5 sandwiches. And we're going to subtract this, 5 slices, from the total that we started with, 8 slices. And so we'll have 3 slices of cheese left at the end of the process. Bread works the exact same way. We started with 20 slices. How many slices do we need to make 2.5 sandwiches? Well, we need 2.5 times 2 slices of bread per sandwich, for a total of 5. And so we'll end up with 20, what we started with, minus 5, what we used to produce the 2.5 sandwiches, or 15 slices of bread. Along with these two things, we'll of course have the 2.5 sandwiches as kind of the products of the sandwich making process. Exact same idea applies to the chemical reaction. We know from determination of the limiting reagent how many reaction events are going to take place under these conditions. It's the smaller number, 0.113. The question is how much of each reactant is consumed in the course of this number of reaction events. The stoichiometric coefficients, remember, tell us how many moles of a reactant are consumed per mole of reaction events. And so, since the stoichiometric coefficient on copper is just 1, we know that 0.113 moles of copper are consumed in the course of this 0.113 moles of reaction events. And so we can subtract this from the starting number of moles of 0.3 for copper to determine that at the end of the reaction we're going to be left with 0.3 minus 0.113, which is 0.187 moles of copper left over at the end of the process. What about moles of nitric acid? Well, don't overthink it. You could actually do the same process of, okay, I started with 0.45, 0.113 moles of reaction events, but I need to multiply that by 4 since 4 moles of HNO3 are consumed per mole of reaction events. What you would find is that that product, 4 times 0.113, simply is 0.45. And of course, just like we saw for the sandwich making process, because HNO3 is limiting, none of it will remain at the end of the process. We can use a similar thought process to figure out the moles of products that are formed in the course of this reaction. And in fact, we did that in the sandwich case, 2.5 sandwiches, right? I won't go through that here, but that's just a matter of applying these molar ratios now, along with the limiting number of reaction events, which we calculated before. Now let's transition to talking about yield. One thing to note about everything we've talked about so far with stoichiometry is that we've assumed throughout that reactions are complete and involve no losses of material. The only way we're able to use molar ratios, for example, is to assume that reactions go to completion, that 100% of the reactants are converted to products. Real reactions are not this simple. We often get less than, for example, the stoichiometric amount of product, the amount predicted from stoichiometric theory. We call that hypothetical stoichiometric amount of product the theoretical yield. This is the hypothetical maximum based on the limiting number of reaction events in a general situation where we have a limiting reactant. The actual yield is an experimental number. It's just an experimental mass, or moles, of product obtained. The percent yield is the ratio of the two. So you can imagine a larger percent yield is better. 100% is the ideal. Greater than 100% indicates that there are impurities in the product that was isolated, and less than 100% indicates that some of the product was lost in the course of the reaction or purification or what have you. So this just kind of shows you in a graphical form what a percent yield less than 100% looks like and what a percent yield greater than 100% looks like. And remember that this extra chunk, and potentially even more of this, for a reaction that yields more than 100% of product, has got to be impurity of some kind. It cannot possibly be, due to the law of conservation of mass, the desired product in its entirety, because we know the theoretical yield of product. That's what's in the black box. Anything more than that must be something else, according to the law of conservation of mass. For a yield less than 100%, this gap between the actual amount obtained and the theoretical amount can be due to a couple of different factors. The first is losses. So, say the reaction in actuality does go to completion, but we spill something on the floor, which happens. In that case, we would call that lost product that we spilled or weren't able to scrape out of the flask or what have you a loss. So that's one possibility. Another possibility is incomplete reaction. Not all reactions actually go to completion. In other words, we may have a situation where the reaction mixture has remaining reactants, even remaining amounts of the limiting reactant that hypothetically would be completely consumed. When we talk about chemical equilibrium, we'll look directly at reactions that do not quantitatively or 100% produce products, and they're actually more common than it might seem based on what we've talked about so far.